Hello, everyone. We're picking back up on Chapter 9. So this is part 2 of the Chapter 9 video for Physics 215, Physics for Scientists and Engineers. I'm Professor Barlow. We're going to pick back up where the part 1 video ended off. We're in Chapter 9, and we're going to start Section 9.6, which is inelastic collisions. Now, we talked a little bit about a brief definition of inelastic collisions. So with inelastic collisions, some of the initial kinetic energy is lost to thermal or potential energy. Kinetic energy may also be gained during things like explosions. So there is the addition of chemical or nuclear energy to it. A completely inelastic collision is one in which two objects stick together after final velocity, so there is only one final velocity. So an example would be a car collision where the cars kind of stay together as they're moving, or a bullet strikes something and embeds itself in whatever it strikes. Those are examples of inelastic or completely inelastic collisions. Okay, so we're going to revisit the train car example as an inelastic collision. So you have two train cars, both 10,000 kilograms, just like before. Okay, car A traveling at 24 meters per second strikes an identical car, car B, at rest. If the cars lock together, how much of the initial kinetic energy is going to be transformed into thermal or other forms of energy? Okay, so we're going to be looking at energy in the initial and final condition. So I'm going to switch to a whiteboard, and we're going to take a look at this. So kinetic energy is equal to 1/2 mv squared. So if we take a look at this, you have 1/2 the mass of the rail car initially is 1,000 kilograms. And we know from what we were given that it's traveling at 24 meters per second. And we square that velocity. So the kinetic energy initial of that car moving down the track, 2.88 times 10 to the 6th joules. Okay, so I like putting a little cloud around intermediate answers. Kind of keeps things straight for me. So this is before the collision. So this is energy initial. But now let's look at energy final, or energy after the collision. We're still going to have the same kinetic energy equation. But if you remember, when we solved this before, the two rail cars are going to lock together. That makes the combined mass 20,000 kilograms. And the speed with which they move together as they're locked together, we figured that out before. It's 12 meters per second. So the final energy of the two cars locked together as they move down the track is 1.44 times 10 to the 6th joules. So what was lost to thermal or noise or whatever is going to be this change in energy initial minus energy final. You're comparing before and after. So the initial was 2.88 times 10 to the 6th joules minus 1.44 times 10 to the 6th joules. So energy transformed into thermal or other forms is going to be 1.44 times 10 to the 6th joules. Let's do another example. Go back to the PowerPoint here. So let's take a look at an inelastic collision in a situation. It's called a ballistic pendulum is what this example is. So you have a block hanging down from a ceiling, and those cables can move left or right. Okay. This is called a ballistic pendulum. So the bullet flies along, it strikes that object, that mass hanging down, okay? And it's going to measure the speed of the projectile, such as a bullet. So we're going to measure, we're going to be able to measure the velocity and derive an equation for velocity of the bullet based on the mass of the bullet and the mass of the block. Okay, so projectile of mass lowercase m is fired into a large block of mass uppercase M, which is suspended like a pendulum. As a result of this collision, the pendulum and projectile are going to swing upward together. So it's going to create potential energy, right? It's going to go up, and that next point in time, you're going to have this potential energy of what the bullet caused the pendulum to go upward, or that height h, lowercase h. So they want us to determine a relationship between initial horizontal speed of the projectile v and maximum height h. Gravity is also going to play a part in this, right? So I'm going to go to a whiteboard again. I'm going to clear this. And so we know that momentum is going to be conserved. So momentum initial is going to be equal to momentum final. Okay. So momentum initial, the block, the large block isn't moving, but the bullet is. So that's our lowercase m times the velocity of the bullet is going to be equal to the mass of the bullet plus this uppercase M, which is that block that the bullet is fired into. And they're going to be moving at some common velocity v prime. So this is conservation of momentum. If I solve this for v, for my initial velocity, which is what I want, so I'm solving now for this, I have m, lowercase m, which is the mass of the bullet, okay. But now what I want to do is, now we also know that kinetic energy is also going to be conserved, okay? So kinetic energy initial is going to be equal to kinetic energy final. Kinetic energy initial is going to be kinetic plus potential is equal to kinetic plus potential in the final condition. Well, in the initial condition, so for our kinetic energy in the initial condition, we're going to have 1/2 mv squared plus there's going to be no initial what we're actually looking at is these 2 points here. Let me stop screen sharing for a second and go back to the PowerPoint. So for the kinetic energy, what we're looking at is this point here where the projectile has made contact and is embedded into the block, and now it's going to force it upward. Okay, so we're looking at this point in time where they are joined, and then after the block has reached its maximum height. So we're looking at this point and this point here. So I'm going to go back to my whiteboard, and our kinetic energy after the bullet has struck the block, it's m plus m, and it's v prime squared. Okay, the block has not, so this is my k, and my potential energy initial after the bullet has made contact and collided, it hasn't started to go up yet. So that potential energy is going to be 0. So now we're looking at the final condition where the bullet and the block have swung upward into the air and gained some potential energy, but they haven't started to swing back down yet. So it's reached the top of its motion. So its kinetic energy in the final is going to be 0. The potential energy now is going to be the mass of the bullet plus the block, GH. So it's mgh, but it's the combined mass of the two objects together. Okay. So now what I can do is I can rearrange and solve this for this V prime. Okay. So the mass of the bullet plus the mass of the block, I have that on both sides. You see that? So that is going to cancel. If I bring the 2 over and solve for this, I get V prime is equal to 2 GH, but I'm taking the square root of that. Now I have a V prime, so my V initial up here that I have for conservation of momentum this V prime, I can take this solution and bring it up and put it in there. And now I will have my initial velocity. So if I rewrite this out, I have V, mass of the bullet, plus the mass of the block, which is coming from here. Now I'm multiplying that by the square root of 2GH, and I'm dividing it by lowercase m. So this is your equation for this ballistic pendulum example, okay? The take-home message here is you're using conservation of momentum and conservation of energy to solve the problem. So now we're going to take a look at collisions in 2 or even 3 dimensions, okay? So now instead of things moving along on one axis, we're now going to look at things going off at angles. So it's not super complicated. We're just going to be adding some trig into what we've already done, and you're going to need to do sines and cosines. Now, I want you to get away from the logic of, well, X is always this and Y is always that. Let the angle that you're given and the triangle that's associated with that angle guide you in terms of whether or not you're using sine, cosine, tangent, whatever you're going to use. And I'll explain that as we kind of go through this example. If conservation of energy and momentum can also be used to analyze collisions in 2 or 3 dimensions. Okay. But unless the situation is very simple, the math can become pretty complicated because now we're doing sines and cosines for everything. Okay, so here, for example, we have a moving object that collides with an object that's initially at rest. So MA is moving, MB is sitting still. Okay? If we know the masses and the initial velocities, okay, it's not enough to just know those 2 things. Now we have to know the angles in between in order to find the final velocities. Okay? But you have all taken enough math now that you should know that, okay, we have momentum, but we have momentum in the X and the Y direction. Okay? So you can solve for momentum in both the X and the Y because you're going to be able to break down this mass A is shooting off at an angle at the end, but this angle that it's shooting off at is going to have a horizontal, an X component, and a vertical Y component associated with it. So you're going to be able to break this up using the angle. And for B, you're also going to have an X and a Y that it can shoot off at. Okay, so if you have 2 unknowns, you need 2 equations. If you have 3 unknowns, you need 3 equations. If you have 4 unknowns, you need 4 equations. So that's what the text is saying where it can get unwieldy. It's not so bad. Let's take a look at what I'm talking about, but have this picture handy as we kind of go through this, okay? So what I'm going to do is I'm going to go back to my whiteboard. And we are going to look only initially in the X direction for momentum. So momentum in the X. So momentum for A in the X plus momentum for B in the X is equal to momentum AX prime plus plus momentum Bx prime. We know that the momentum for B is 0 because it is initially at rest. Both objects are going off at different angles and at different velocities after this collision. But now at this point, I can plug in MA VA is equal to MA VA prime. I'm going to stop sharing for a second because I want you to take a look at something. We're looking at this angle, theta A, okay? We're looking at the x component. So for this example, if I'm looking at the x component of momentum for A after the collision, the x-axis is adjacent to theta. The y-axis is going to be opposite to, because it doesn't matter if I look at this component here or over here, okay? The y component is opposite the angle. The x component is adjacent to it. So with that said, hopefully it's pretty obvious that the x's in this example are cosine theta for A, plus the momentum for B, MB, right? VB prime cosine theta B. And the other thing that I want you to take a look at is I want you to take a look at in the x direction after the collision. Both A and B are going off in a positive x direction. Okay. But notice that A is going off in a positive y direction, but B is going off in a negative y direction. You're going to need to keep track of those signs based on your picture. Okay, based on your free body diagram, based on the sketch that you're given. So you're going to need to track the signs also, but it just so happens that A is going positive in the x-axis initially, B sitting still, then they're both going off in a positive x direction. So back to the whiteboard, cosine theta B, okay? So we're going to do the same thing, but now we're going to do it for y. So you have PAY plus PBY is equal to PAY prime plus PBY prime. Now, initially, neither one is moving vertically. So both of these are going to be 0. Okay. Then you have MA VA prime sine theta, because it is opposite the angle. And remember what I said, it doesn't matter where you're looking at that triangle, right? So what do I mean by that? So if A is shooting off this way, and we're looking at PA prime, and this is my angle, here's my x, so that's adjacent to this. The vertical component of y, I can look at it here, I can look at it there, it doesn't really matter. If I look at it here, you can see that it is opposite, hence sine. Okay. Now for B, take a look at B. mass B and momentum B, you have mass B, V prime of B, sine theta of B. Now, I have the negative here, okay? You could say that this is positive, and when you do the math over here, let's say the angle that I gave you for B was 30 degrees. At that point, you can say negative 30 degrees because it's going downward from the x-axis. Or you can say that the sign here is negative and that it's positive 30 degrees. Don't double count it. Just recognize that this component in the y direction for B after the collision is going off in a negative direction, okay? So just be careful with this sign that you account for it, but don't double count it, okay? So I'm going to stop sharing for a second. Go back to the PowerPoint. Okay, so now I have two equations for the x and the y. Okay, so we're going to stick with this example. Okay, but now we're going to put some numbers to it. So we're going to say that billiard ball A is moving with a speed VA is equal to 3 meters per second in the positive x direction. It is going to strike a ball with equal mass. Okay, well, that helps. Okay, but we could make the masses unequal and carry the signs through. The two balls are observed to shoot off at 45-degree angles to one another on the x-axis. Ball A above the x-axis, ball B below. So theta is 45 degrees positive, or theta B is 45 degrees negative. We are tasked with finding the speeds of the two balls after the collision. Okay. Well, let's go back to our whiteboard. And take a look at this. So you have MA VA is equal to MA prime cosine theta plus MB cosine theta. Okay. So we have that. And we also have, so this is my first equation right here. And we have our second equation, which is right here. Clean this up a little bit. Now, what I'm going to do is I'm going to solve this equation here for VB prime. So rearranging this, I get VB prime is equal to negative VA prime, because I have to move it over to the other side, sine 45 degrees divided by the sine negative 45 degrees. On your calculators, you want to make sure that you're working in degrees, not radians, but hopefully you guys already knew that. So now I have an equation solved for VB prime that now I can take and plug back into this equation up here. I'm plugging it in for this VB prime right here. Okay. But what I'm doing is I'm also given that the MAs and MBs, the balls are equal masses. So I can get rid of that and then solve this. VA is equal to VA prime cosine 45 plus VB prime cosine 45. So this, if we solve it out before I do the substitution, is going to be 2 VA prime cosine 45. We know because they're going off at 45-degree angles to one another, VA prime is going to be equal to VB prime, which is going to be equal to VA over 2 cosine 45. So our initial velocity is 3 meters per second. And cosine 45 is 0.707. So VA prime is equal to VB prime, which is equal to 2.1 meters per second. Okay. I'm going to go back to now we're going to do an example where we have a proton traveling at a speed of 8.2 times 10 to the 5th meters per second. Okay, that's A. And it collides elastically with a stationary proton. Of the protons observed to be, they're scattered at a 60-degree angle. Okay. One of the protons is observed to be scattered at a 60-degree angle. At what angle will the second proton be observed? And what will the velocities of the two protons be after the collision? Okay. So, one thing that we need to do right away is we need to establish that MA in this example is going to be equal to MB. Okay, so that's going to help us out a little bit here. Okay, so the first thing we're going to look at is conservation of momentum. You have P A in the X plus P B in the X is equal to PA x prime plus PB x prime. We know that B is stationary initially because it's our target, so that's going to be 0. So you have MA VA in the X is equal to MA VA prime cosine theta A plus MB VB prime cosine theta B. And you can do the same thing for the y direction. But because we know that the masses are equal, we know these masses will drop out. So in the x direction for momentum, we have VA in the x is equal to VA prime cosine theta A plus VB prime cosine theta B. So we also have kinetic energy to deal with. So this is momentum on the left, and we're going to take a look at kinetic energy here on the right. So kinetic energy, initial, you have 1/2 M A VA squared. There is no MB because it's got 0 velocity, so I'm not even going to write that down, is equal to 1/2 MA VA VA prime squared plus 1/2 MB VB prime squared. Okay, well, what happens here? We have 1/2 MAs and 1/2 MBs. We said that MA is equal to MB, and 1/2 is a constant all throughout. So all of that cancels. So you have VA prime squared sorry about that. You just have VA squared. So your initial velocity squared for VA is equal to VA prime squared plus VB prime squared. If I rearrange this, I could get and solve for VB. VB prime squared is equal to VA squared minus VA prime squared. So now I have a value for VB prime squared, okay? But I also have a value for okay, so what we're going to do now is we have this VA, we have this equation here, okay? And then we also can do the same thing for the y direction and determine that it's going to be 0 is equal to VA prime sine theta plus VB prime sine theta B. So this is my second equation. And we also know from over here, from this solution, VA squared is equal to VA prime squared plus VB prime squared. So now I got three equations here. So now what we're going to do is for these two equations, notice how on the equation on the right, everything is squared. So if we take these equations here, what we're going to do is we're going to solve them in terms of VA prime. We're going to move that to the left side, right? So we're going to bring this VA prime in both cases out and over to the left side. And then we're going to square both of the equations. So we're going to take this and square it. We're going to take this and square it. And what you end up with is you have VA squared minus 2 VA prime cosine theta A plus VA prime cosine squared theta A is equal to VB prime squared cosine squared theta B. And if we do the same thing with the bottom one, we get we do the same thing with this bottom equation. We get VA prime sine squared theta A is equal to VB prime squared sine squared theta B And now what we know is we have the trig identity sine squared theta plus cosine squared theta is equal to 1. And if you look here, you have sine squared plus cosine squared. If I add these two together, this just becomes 1. So then adding this to this, right, you end up with VA squared minus 2 VA prime cosine theta A plus VA prime squared right? Because you also have sine squared plus cosine squared is 1 right here and right here. And that is equal to VB prime squared. Now, if we substitute this right here down into this, you have this VA squared minus this is this. So by substituting that into that, you end up with 2 VA prime squared is equal to 2 VA prime cosine theta A. So what happens then is after that, one of those VA, 2 VA, or one after one of those VA squareds cancel, you're left with VA is equal to VA cosine theta A. So your initial velocity is your 8.2 times 10 to the 5th meters per second times cosine 60 degrees. So VA prime is equal to 4.1 times 10 to the 5th meters per second. So that's VA prime. Okay. Now, what we're going to do is we can rearrange this equation right here. I'm going to clear my whiteboard, but I'm going to go back to that equation now and solve that for VB prime, which is equal to the square root of VA squared minus VA prime squared, which if you solve that, VA is your 8.2 times 10 to the 5th meters per second. And we're going to square that minus VA prime, which we just solved for, is your 4.1 times 10 to the 5th meters per second squared. Square the whole, take the square root of the whole thing. VB prime is 7.1 times 10 to the 5th meters per second. So you got 4.1 and 7.1. Now to solve for the angle, you can use pretty much whatever trig function you want. I'm going to use sine theta b is going to be equal to negative VA prime VB prime sine theta A. So that's going to be your negative 4.1 so we know that it's going to be negative. (4.1) times 10 to the 5th meters per second over 7.1 times 10 to the 5th meters per second. The sine of 60 degrees is 0.866, which you get sine theta prime b is equal to 0.50, which theta b is equal to negative 30 degrees. So 30 degrees, but downward from the x-axis. Okay, so you can see how some of this can get quite a bit unruly, but the take-home message is, you know, momentum is mass times velocity, and if it's going off at an angle, you're just using your sines and cosines to break things into their x or y components depending upon where that angle is located. Okay, so that's really the take-home message there. So when you're solving collisions in 2 or 3 dimensions, choose a coordinate system. If it's really, really complex, you can choose a sub-coordinate system, a subsystem, where you can apply the laws of conservation of energy like we did in the last one. Are there any external forces acting on this stuff? If it's a short enough time frame, can you ignore it? Draw diagrams of both the initial and final conditions with momentum vectors labeled. Okay. Choose the coordinate system. So choose a coordinate system, all right? Choose an initial system for where this whole law of conservation of momentum applies. Are there any external forces? Draw your diagrams, choose a coordinate system, apply momentum conservation. There will be one equation for each dimension. So you're going to have an x and a y direction. And then you can also have an initial and final condition as well as the X and the Y direction. So you could have up to 4 equations and 4 unknowns, but we wouldn't get into something like that on the test. If the collision is elastic, apply conservation of kinetic energy as well. Solve it, check for your units, check to make sure that it's logical. Okay. Let's start talking about center of mass. So center of mass, okay, for things that rotate, if you have rotational motion, whatever is rotating is going to rotate about its center of mass. So if you have this diver, okay, that jumps straight up and down, like in this diagram or in this figure here, we've all seen little kids at the pool, you know, do this type of jumping, right? This is purely translational motion. It's going from point A to point B. They're doing it in an arc, so they're acting like a projectile. It's projectile motion, but there's no rotation happening. In figure B, this is more like a competitive diver who's rotating. As this diver is doing their dive, they're rotating about their center of mass. There is one point that moves in the same path that the particle would if subjected to the same force as the diver. That point is called the center of mass. Well, let's look at a different definition of that. Center of gravity and center of mass of an object. The point at which the force of gravity can be considered to act is the center of gravity. The force of gravity acts on all parts, and you can assume a summation of all the points to get one point. So in most cases, center of gravity and center of mass are the same thing. The only difference is for an object that is so massive, that is so huge, that the acceleration due to gravity would be different at different places on that object. Okay, but for the most part, center of mass and center of gravity are synonymous. Okay. The general motion of an object can be considered as the sum of translational motion plus rotational, vibrational, etc. Right? So if you throw something like a wrench, a knife, it's going to rotate about its center of mass. Okay? So for two particles, any two particles, the center of mass lies closer to the one with the most mass between the two. Okay, so the simple equation for center of mass is ma distance xa, and that xa dimension can be measured from really any location. I'm starting from an arbitrary xy position, but it can be a point on an object also, or it can be like a reference frame out in space, right? So to determine the center of mass in the x, you're going to take this mass for this object and multiply it by its distance away from this origin. This mass of this object multiplied by that distance away from its origin, divided by the summation of the two masses, or the total mass of the system. Now, in general rules, you can have 3, 4, 5, you can have MC, XC, MD, XD, and then this lower, the denominator would be the sum of all of those. So let's look at this a little bit in an example. Okay, so this, we have 3 people riding on a banana boat. Okay, so 3 people are riding this banana boat. We're going to say they're the same mass. Okay, just for this example. They sit along this banana boat. So from the back end of it, we're going to say is 0 in the X, you know, for measuring our distances. So person A sits 1 meter in from the end. person B 5 meters, person C 6 meters, all measured from the left end. Find the position of the center of mass of this object. Okay, so back to our example. I'm going to so like I said, here's your equation that we just went over, okay? And then here's our banana boat example. So now let's take a look at solving this banana boat example for the center of mass in the x direction, okay? So the x center of mass is going to be equal to the mass of person A, XA, plus the mass of person B, XB, plus the mass of person C, XC, right? Divide all of this by M plus M plus M, right? So the denominator is now going to be 3M, okay? So what I can do now is I can factor out a mass out of the numerator, and it's XA plus XB plus XC, because these masses are the same. And I'm going to divide this by 3M, okay, because there's 3 of them. The M's cancel. The distances that I was given were 1 meter plus 5 meters plus 6 meters, all divided by 3. So my X center of mass is going to be equal to 4 meters. Okay. You can also look at center of mass in terms of two dimensions or even 3 dimensions. Okay. Center of mass, 3 particles in 2 dimensions. Okay. We have 1 particle at the coordinate center for X and Y, at the center of the X and Y axes. We have, so out here, and then we have mass B, and then mass C. Mass B is 2 meters out, and mass C is 2 meters out and 1.5 meters up. Okay, so the center of mass for this thing, they gave us a nice little sketch. It would roughly be in this area. Okay, so 3 particles, each has a mass of 2.5 kilograms, are located, you know, at 2 meters over and 1.5 meter up for C, 2 meters out for B, and MA is at the center of this coordinate system. Okay, so let's solve this for both the X and the Y axis. So I'm going to switch to my whiteboard, but it's a good idea to have this figure up, or have your textbook in front of you, or have the PowerPoint open at the same time as I'm solving this. Okay. Right. So the X center of mass is going to be the first mass, which is 2.5 kilograms. Its distance out from the X position is going to be 0 because it's right at the center of where the X and the Y axis were. particle B, 2.5 kilograms also. This one is 2 meters out in the X, plus 2.5 kilograms. Particle C is also 2.5 meters out in the X direction. So these are the X directions. So they're X distances. Okay. So 2.5, 2.5, and 2.5 is 7.5 kilograms. So if I solve for the X center of mass, I get 1.33 meters. The Y center of mass is equal to 2.5 kilograms, also multiplied by 0, 2.5 kilograms. Now, if you look at particle B, it is also a distance of 0 away from the X or going up the Y axis. Particle C is 2.5 meters and it's 1.5 meters. I'm sorry, it's 2.5 kilograms. 1.5 meters up in the Y. So there's your 7.5 kilograms. So our Y center of mass is 0.50 meters. Now, in the picture, it asks for a resultant center of mass. Well, the resultant center of mass, we have an X and a Y, which is 1.33 in the X squared plus 0.50 squared, square root of them because, Pythagorean's theorem. So the resultant center of mass in a straight line from where the X and Y coordinate system origin is 1.42 meters. Tan theta is 0.5, which is opposite over 1.33. So the angle would be 20.6 degrees. Okay. So now if I go back to my picture, the center of mass is located 1.33 meters over in the X and 0.5 meters up in the Y. The resultant is 1.42 meters up as a straight line, and this angle here would be 20.6 degrees. Okay? Okay, so that wraps up the center of mass example with the 3 particles. So for an irregular shaped object, we can imagine making it up of a group of an infinite number of tiny particles, each with a tiny mass, adding up the product of each particle's mass with its position and dividing it by its total mass. It's basically an integral, right? In the limit that the particle becomes infinitely small, you have the centroid is equal to 1 over the total mass, the integral of this resultant dm. Okay. You can show that the center of mass of a uniform rod length L at its center by using that integral. So we're not really going to do that in this class. You will get to that if you have a statics class. But let's look at, you know, a more conventional shape here. So we have this L-shaped bracket, okay? This L-shaped bracket is uniform. It is thin. It is L-shaped, okay? And we're going to say it has a thickness and a density, okay? If you have 3 dimensions of something, an X, a Y, and a Z. So if you imagine this L-shaped bar coming out of the screen to you, you can imagine that it has that thickness as well as a density. So something that has 3 dimensions. So if you have a cubic volume of something multiplied by its density, which is its weight per cubic I'm sorry, I'm drawing a blank here. If you have the density of something, which is like pounds per cubic foot, okay? So if you have its weight per its cubic dimensions, right? Its volume. So it's weight per volume. So density is weight per volume and is given by the symbol rho. So let's do this center of mass example, okay? So we know that from the drawing, XA is going to be 1.03 meters because it's halfway over from the 2.06 meters. If you look at where the X and Y coordinate system, YA is given by 0.10 meters, okay? So the mass for the upper part, A, is going to be 2.06 meters times 0.20 meters times whatever its thickness is times this density, which is rho. So you have 0.415 meters squared thickness rho. And if we do the same thing for the other part of the bar, the vertical part of the bar, that's 1.48 meters long. It's also 0.2 thick times its thickness times its density. You have 0.296, its thickness times its density. So what we do to get its center of mass in the X direction, so I'm going to do the X direction first. X center of mass is equal to your 0.412 times rho thickness times 0.1 plus 0.296 times negative 0.74 meters. Because if it's if it's 0.2 thick, right, we want to know the X position of that part B, right? That's going to be negative 0.74 down, which is the 1.48 divided by 2. So that's rho T times 0.078 meters squared So these rho t's will all cancel. And we're left with an X center of mass or I'm sorry, this was the Y. This was the Y center of mass. So your Y center of mass is negative 0.25. Your X center of mass is going to be 0.412. Now the rho t's are going to cancel out just like they canceled out before. Your X center of mass is 1.03 for the upper part, or for the horizontal piece. The vertical piece is going to be your 0.296. But that is 1.96 meters. The reason being is, if you look at the picture, it's 2.06 to the end of it, but half of that 2/10 is 1/10. 2.06 minus 0.1, that's where the 1.96 comes from. And it's also divided by 0.078. So the X center of mass is equal to 1.42 meters. So a little bit beyond the center of that at 1.03. Okay. And if we go back to the PowerPoint, here, you can see they kind of gave us a little picture of this, and that's the 1.42 meters over and negative 0.25 meters down. Okay. So another way to determine center of gravity is the point at which the gravitational force can be considered to act. That's another definition for it. It's the same as the center of mass as long as the gravitational force doesn't vary among different parts of the object, like I was saying about a massively heavy object. So if we have a pivot point and we take this object and we suspend it from a whole bunch of different pivot points experimentally, okay, and you draw vertical lines as it's suspended from this pivot point, where all of those lines intersect is going to be the center of mass of that object. Okay. You're not responsible for section 9.9 at all. You're also not responsible for section 9.10 at all. So to summarize, momentum is, it's a pretty simple equation. Momentum, lowercase p, is equal to mass times velocity. It relates to Newton's second law. Sum of forces is equal to change in momentum with respect to change in time. Total momentum of an isolated system is conserved. During a collision, the colliding objects can be considered to be an isolated system, even if external forces exist, if they are not too large. Momentum will therefore be conserved during collisions. Impulse is defined as, is given by J, and it is defined as the integral of force with respect to change in time. In an inelastic collision, some kinetic energy is lost to other forms of energy, right? In an elastic collision, total kinetic energy is conserved. Completely inelastic collisions are ones in which the two objects stick together or one's embedded inside the other after the collision. The center of mass of a system is the point at which external forces can be considered to act, and that brings us to the end of chapter 9. Okay. Again, as always, come to the Zoom meetings prepared with any questions. The only thing that is tricky about momentum is when you start having things go off at angles and directions and you have different masses. And it really boils down to keeping everything sorted out in the initial condition and final condition. And if things are going off at angles, assigning the correct sine, cosine with it and making sure that, okay, is this continuing positive in the X and one's going positive Y and the other one's going negative Y? So, you know, conservation of momentum and conservation of kinetic energy are going to be what you're going to use to solve most of these problems. So that brings us to the end of chapter 9. Like I said, come to the Zoom meetings prepared with any questions. Thank you, and we'll see you for chapter 10.